we propose a novel solution to robustly detect wireframes beyond challenging large occlusions. Wireframe is a line segment-based representation designed to well capture large-scale visual properties of regular, structural-shaped man-made scenes surrounding us. However, we often face that the underlying scene is occluded by a foreground object that may be too large to ignore easily. Unlike wireframes, conventional edge or line segment detection methods focus on all visible edges and lines, producing spurious results not well aligned with the salient structure of the scene. Existing wireframe detection methods are not designed to predict hidden structure beyond the occlusion. On the other hand, our approach knows to predict wireframes well aligned with salient structural information of scene across the large occlusion. This figure shows a popular basic framework for wireframe detection. Its backbone predicts junction and line maps, which are then converted to coordinates and matched to get line segment proposals. Each proposal is verified to obtain final line segments with scores assigned. However, models from this kind of framework are yet unable to handle large hole occlusion. Our solution introduces three novel ideas to make the basic wireframe detection far robust to large hole occlusion. This even improves the performance without hole. Let's talk about each module of our novel approach in detail. First, we introduce a new conditional data generation method and training techniques to let the model understand holes. We transform a training dataset with wireframe annotation into conditional data by superimposing a real foreground silhouette onto each image and pairing it with a corresponding binary mask map. We also carefully control the size and placement of the superimposed holes during training, which leads to effective conditional learning with respect to holes. Second, we combine RGB generative adversarial network that learns to regenerate invisible scene contents inside the hole. Our generative adversarial network encourages the model to better predict the underlying hidden structure of the scene even beyond the hole. Finally, we introduce semi-supervised learning with pseudo labeling to further the enlarge model capacity to overcome small-scale ground truth labels. Our approach can be flexibly combined with any of the recent basic frameworks that share a similar backbone network. Let us compare results from existing models and our approach qualitatively. Here we created input test images with hole by superimposing real foreground silhouettes onto standard wireframe test set images. The size of each superimposed silhouette is up to 30% of the input image's entire pixel area. HTLCNN, HTHAWP, and FClip are recent best models for ordinary wireframe detection without hole. However, these models are not designed to handle large hole occlusion. These existing models may leave an empty area where the hole is, or mistakenly detect false line segments around the hole boundaries. On the other hand, our model understands the hole occlusion and underlying structure behind it, producing robust detection across the large hidden area. Let us show a few more examples from this test set with hole. Again, ours detects wireframe far more robustly than existing models. We also found that our approach improves the performance on ordinary detection without hole as well. Let us show some real-world examples where the scene is occluded by a significant foreground object. Here, we created a mask of the occluded region by using panoptic segmentation, as shown in red on the image, and applied it to our model. Existing models may fail to detect wireframes across the foreground region in the photo. Unlike existing models, our model detects wireframes across the occluded region robustly. We evaluated our model comparing with recent existing models on standard wireframe test set with and without hole. Our model shows the best performance as shown in the table, dramatically better with hole, and meaningfully better without hole. Please note that even 1-point score difference of the structural AP metric is still considered to be a lot in the wireframe detection task without hole. The PR curves on the structural AP 10 metric more clearly demonstrate that our model outperforms existing models compared with. Note that a red curve indicates our model. Here we show an ablation study with respect to three main parts of our full approach. Applying our conditional training and RGB generative adversarial network already improves the performance dramatically, as indicated by a green curve. By applying pseudo labeling additionally, the performance is even further improved, as shown with a red curve. We can still confirm performance improvement on the ordinary detection without hole, in the same order.